Max Seeley embarked on his career in electronic design and robotics in 2001. Since then, he has cultivated his expertise in electromechanical systems, autonomous robotics, and PCB design. In 2013, he joined IMRIS as part of a technical team whose objective was to develop the Simbus surgical system, an intelligent robotics-assisted system capable of minimally invasive procedures and advanced imaging. Currently, he serves as lead electrical engineer for the Digital Systems Group, part of the Corporate Research and Development Lab at 3M. As lead engineer, he oversees the development of high-performance small form factor electronics. Max is also a certified Altium instructor for 3M and has led numerous training courses demonstrating best practices with Altium Designer solutions. Ladies and gentlemen, please welcome Max Seeley.
I'm Max Seeley, and I definitely want to get a copy of that so I can play it at every meeting I attend at 3M. Because one of the things I know back, my coworkers love pranking me when I'm out of town. Last time I was at a conference, I came back to a mannequin in my cubicle, and then about every free office chair in the office was piled up around my desk, and so this will let me exact a little revenge against them. I'm not going to, let me tell you about what I do on a daily basis at 3M. And so my title is Senior Electrical PCB and Manufacturing Engineer. And so I'm in the unique position at 3M where I design circuitry, but then I take that circuitry and I implement it in a printed circuit board. And in doing that, I perform and lead all of the signal and power integrity analysis that happens to that circuit board during the layout process. I am also the interface to our outside partners that help us fabricate those circuit boards in prototype and in production. And I think that, you know, being in that role or having someone in that role that has visibility and insight into the entire process is extremely valuable, and it's produced results at 3M. And so what I'm going to talk about today is schematics. And in particular, I'm going to talk about how schematics contribute to a robust PCB layout. But then I'm going to talk about just some general things with schematics and some best practices with schematics. And why am I going to talk about these things? Well, number one is you know, being methodical about schematics will help you reduce design cycles. And you know, ultimately that's going to save money, and I don't think that's a hard connection to make. But for instance, on the last board I designed, the rush turn time on getting that board spun was 28 days. And not only that, but kind of to the second point, when we got the board in, it is an exceedingly difficult board to probe. There are, you know, some methods that we can use to get at some of the signals in the DDR bus. We can put in interposers, but we really have to be methodical about designing this thing because there are serious limitations on what we can do with the board once we've gotten it. And then I truly believe, you know, one thing I want to say, and then it's going to sound a little bit self-aggrandizing, is all of the boards that I've been involved with designing have, for the most part, worked on the first turn. There are always some modifications that come in that need to be implemented when we commercialize, but all of the boards I've designed have worked. And they have all passed FCC Part 15 on the first try. In fact, the last board that I designed, when they put in the chambers at 3M, to do the pre-scans, they had to check the equipment to make sure it wasn't broken. The reason I believe that I've been successful at doing this is because I am methodical about my schematics. And I realize that a lot of people in this room are PCB designers. And you might be saying, you know, I don't do the schematics. The electrical engineer throws them over the wall, and I do the layout. Well, what I would say to that is, number one, as the PCB designer, I promise you, you can have incredible influence over how the electrical engineers produce their schematics, and especially if you can show them results. If you can show them that a little bit more time on the front end, being a little bit more methodical about how they do things, results in getting things done right the first time. The other thing I would say, and I think Altium is partly to blame for this, is if you are a PCB designer, I would warn you that electrical engineers are coming for your job, because it is getting easier and easier for electrical engineers, because the tools are easier to use, for electrical engineers to do layout. Now, what I would say is don't get discouraged by that, because when I'm looking at resumes, one of the primary characteristics I look for on a resume is, does someone have experience with Altium Designer? And two of the best electrical engineers I ever worked with in my career were mechanical engineers who had learned electrical engineering. And so if you are a PCB designer, then push your boundaries. Learn signal integrity, learn power integrity, branch out and start learning the fundamentals of electrical engineering. Go back to school and get a degree in electrical engineering. But the people who really understand PCB layout and understand how to produce a high-speed board are really the next generation of electrical engineers. The days of throwing it over the wall are over, because you can't, the boards are too complicated, and the printed circuit boards have become, in my opinion, the most critical part of the entire circuit. And if not designed properly, nothing in the design will work. What are the essential elements of schematics? Number one is they communicate design intent. And when I say communicate design intent, I want to talk about what I mean by that. I don't mean to other electrical engineers that have been involved in the project from the beginning. I mean that the PCB, whoever's doing the PCB layout can understand the intent of the design. Someone who's not electrical savvy can get an overview of the intent of the design. And too often, you know, I open up a set of schematics, and I have to go back to the engineer that created those schematics and say, why did you do this? You know, I don't understand what this part of the circuit does, and they have to explain it to me. Well, what happens when that person's gone? The schematics are the blueprints for the entire design. And again, I'll hit on this point a couple of times in my presentation, but what I advocate is that if you want to know a piece of information about your design, you go to the schematics. It used to be that you had to go to 10 different documents to get the critical information that you need about the design. But I would say with a lot of the, and you can thank Altium for this too, because Altium really led in developing supplier links, really led in making it very easy to put in critical information about your design into the design, and I'll show that in my presentation. The other thing about schematics is you want them to promote design reuse. And I'll talk about this, but one of the key elements to promoting design reuse is that you make your your design modular. You make it functional blocks, and you can take that functional block and just push it into another design with minimal changes. I think one of the more important elements of schematics are that they contribute to robust design analysis and reviews. You know, that the critical information is in there, that the design can be partitioned and given to many parties to review simultaneously. And let me show you an old style schematic. I have no idea what this does. I can't ascertain it from looking at the schematic. I mean, I can start looking at various, subsections of the circuit and figure it out. But ultimately, overall, I cannot figure out what this does. I don't know, except for some of the logic elements on here, I don't know what these ICs do. So essentially for me to determine design intent with this design, I have to have multiple documents at my disposal and a lot of time. And one of the primary, attributes that I hear exemplified about this schematic, or this type of schematic, and I don't see many schematics like this anymore, but we do see it at 3M. We've got some engineers that have been there for a while. And one of the things that I hear as a plus of this type of schematic is, well, I can see how everything's connected. Really? Because I can't, and maybe, it's the way my brain works, but I lose any kind of insight into connectivity in this very quickly. So is there a better way? So I'm going to start off with a fairly benign schematic that I have in all of my schematics, but I think it's critical because we talked about communicating design intent. And I think it is really critical to have a title page in your schematic. And not only that, and what this is going to do is it's going to give people the ability to easily find what schematic a particular portion of the circuit is on. And this is from Fidevil Academy. Anybody that's taking pictures, and this is downloadable. I took the courses, great courses, and this is for the IMX6 Rex reference design. And we really like the title page, so we use it at 3M. So one thing I want to point out is that the schematics in this first column here are all informational schematics, except for maybe the top level schematic, which is a pseudo schematic. The rest of these are all informational. And in any of our high technology designs, I include all of these informational schematics. The other thing I want to talk about is the design notes right down here in the left-hand corner. And I think this is a great template for design notes. Let me show you those in closer detail. And so these are notes that you will put throughout the schematic. And we've got notes in here that are for just general information, some cautionary notes, some critical notes, some notes for your firmware engineers, and then layout notes. And one of the things that I would really advocate is if you're doing something in layout that is unique, document it back in the schematics. This is an example of where a layout note, a schematic note would have been very helpful for us. So this was a reference design that we used We thought that the vendor that provided this was just giving us options by providing a oscillator and a crystal for the clock input on the processor. What we discovered after we spun the board for the first time is that the processor, the revision 1 silicon, was not capable of driving a crystal. There was a flaw in the silicon, and so they needed an oscillator. And so I went with the crystal because it was more power efficient, and it ended up costing us a fair amount of time. And a simple note, it's interesting, I mean, they had some notes in here, but a simple note would have helped us avoid that. And I realized by putting this in my presentation that I'm still a little bitter about it. The next schematic that's informational, and the next couple of schematics I'm going to show are really related to power. Put a power tree in your schematics. Show the interconnectivity between all of your power sources, where power comes into the board. Where does it go after that? Where do those devices supply power to? And I have some spreadsheets that follow this where you can kind of, ascertain this information from looking at the spreadsheets. But my mind works much better with pictures. In addition, I show on this PMIC, I show, what is the program voltage output for each switcher or LDO on that PMIC? How much current is that particular output capable of supplying? And yeah, some of these documents are time-consuming to generate, but they pay off in the end. And a lot of them are interrelated, so once you start generating one, a lot of the stuff that you generate from one can be plugged into the other. So this is the next one I create. And this shows all of the different voltage rails on the board. And if I look at what voltage range are they capable of supporting? What voltage do I have them set at? What's their power on sequence? What's their maximum current that they're able to deliver? And then I look at, sorry, I keep hitting the wrong button here. I look at, all of the sinks on that particular rail, and I look at, what percentage of available power am I consuming on that rail, and are there any rails where I'm running them too hot, basically. This is another schematic I do, and this is the sinks, and this one feeds back into the previous one I showed. But this one will really assist you with any PDN analysis that you do, because it shows you for a particular rail, what are all the sinks on that rail, and what are their power consumption. And so by having this in the schematic, number one, you have to do this at some point. I mean, if you're going to do a PDN analysis, you're going to have to do this. You're going to have to look at the sinks on a particular rail. But it gives you something to refer back to. You're not kind of just doing it, flying by the seat of your pants. And so hopefully, if there is a mistake, someone else is looking at this document too and catching it, and it's not something that you have just plugged in as a value into your analysis and produce results that are wrong. Because what's the point of simulating? I mean, to me, I would rather not simulate than simulate something in my design and get the wrong answer and be presenting that as a characteristic of my system when it's incorrect. Graphically. So I graphically, in our designs, like to show the power on sequence. And this is for, this really helps in debugging. If you've got any kind of issue with the board and you're trying to figure out if there's a power on sequence issue, and your engineers are sitting there trying to probe 3 or 4 voltage rails simultaneously, it's really helpful to be able to look at a graphic to see how those rails should be coming up. In the PCB, or I'm sorry, in the schematic, put in a 3D representation of the board you're making. And I'm not talking a 3D model. This is a, I used the clipping tool in Windows to clip this, and then subsequently what I will do is bring it in Microsoft Paint and label some of the critical things on this. And again, it's about communicating design intent. And it really allows someone who doesn't have SolidWorks or doesn't have Altium Designer to see a 3D representation easily of what your board looks like. The I/O mux. So one of the things that, and I refer back to this schematic all of the time in the design process, and I cheated a little. So this is for a IMX6 processor, and they were kind enough to do it. Thank you, Freescale, NXP, Qualcomm. I don't know what to call you guys anymore. They were kind enough to put in their reference schematics, and I just copied it. But we refer back to this all the time. And you can refer back to this for, routing your PCB. I mean, I would love to set up pin swapping, try and set up pin swapping for this in Altium, but it would be too cumbersome. So, but, if you're routing out a processor and your I2C4 is on the opposite side of the processor that it needs to be, you can look back at this and see if there's any pins on the side of the processor where you'd like it to be there that can be muxed as I2C. And just in case there's anybody that's looking at this wondering what I'm talking about, on modern processors, the pin function can be changed in the bootloader. And so I can say, all of these functions are basically available for a single pin. One of the things that we do early on in our design is we bring in a FAE from TTM for our advanced designs, and we sit down with them, and we figure out, what does our board stack up? And how are we going to achieve the controlled impedances that we want for our board? And it's a process. And I really appreciate TTM for working with us as patiently as they do and answering as many questions as they do when we're going through this process. But a lot of times what I see happen is people get these informational sheets from the PCB vendors, or they do it themselves. And I would not advocate doing it yourself, because what I have found is that TTM does it differently than the way I would do it. I would use equations to derive my characteristic impedances. With a given dielectric constant, how thick does my substrate need to be? What's the width of my trace? All of that. Or I have tools I can use. But what I have found is that TTM's calculations are always, they're not calculations, results are a little bit different than mine. And the reason why is they're using historical data. My equation attempts to fit the data as best as possible, but it does not fit it perfectly. They're using historical data to derive these values, and so they're more accurate than what I could do. So I don't try and calculate it myself, and if I can get someone else to do it, why not? This is one of the biggest sources of design rules in your project, this document right here. Okay, I have a set of design rules that are pretty transferable between my high-tech designs, except for these. These change with every high-tech design I do. You know, I might try and reuse some of my stack-ups, but this is where I'm going to generate a ton of design rules for my differential pairs, for my layer pairs, or I'm sorry, for my via pairs, for my controlled impedances. And so, to me, you know, taking this and just manually creating design rules and then setting this sheet of paper on my desk again is a real recipe for disaster. Put it in the schematics. I mean, allow someone else to review what you've done and not by, you know, kind of chasing your tail. And that, you know, a lot of times what we do is we put this in the stack up in Altium Designer, and we generate, you know, a diagram from Altium Designer, but those are the values that we put in, and we use that diagram to check the stack up. I mean, that's not going to work. So, my top level document, or my top level schematic. You know, as I hope a lot of you in here have used hierarchical design capabilities in Altium Designer. But this is where, to me, you know, that criticism of that benefit to that super crazy old schematic was that you could see connectivity. I don't know about you, but I can see connectivity a lot clearer when I look at this. And this is where I find my connectivity. And there's a couple of things I do. I color code my sheets. So I've got one in there. All of my power delivery elements, part of my PDN, are yellow. All of my connectors are light pink. All of my memory elements are blue. And then just all my general circuit elements are green, and then my antennas are purple. And if you've got some element that you want to differentiate, come up with a new color and come up with your own scheme. You don't need to use my scheme exactly. But the point is that I can easily identify some critical elements or some critical types of elements in my design by looking at my top level schematic, and I can also see, you know, the overall connectivity of my design. Here's the other thing for, you know, PCB designers is I look at this and I can imagine in my head how I'm going to partition my design, how I'm going to organize my board by looking at this. And to me, board organization, I will tell you, you know, and I agree with Dan on so many things, but splitting grounds is a disaster. You need to smartly partition your design to mitigate a lot of the issues that people would split grounds to try and mitigate. So this would correspond to a green, light green sheet symbol. And you know, what I want to emphasize about this is, while I think it's important to see connectivity in a design, I would also argue the converse. I would say that connectivity doesn't matter. Okay, you can look at this element, this functional block that I can reuse over and over again, and look at it as a black box. I don't care where it goes. I care about what comes in and what goes out. And from there, you know, I can treat each one of these as functional blocks. The other thing I do in my designs, you know, using a lot of the features in Altium Designer, is I put in information about any design choice I made in this functional block. So, for instance, I'm not going to hit the wrong button this time. This is a truth table for the EN inputs on this. And it tells me, depending on their configuration, what the output charge current limits are going to be for this charge management IC. This is the table that shows by this selection of resistors what my charging limits, what my thermal thresholds are going to be for charging for this particular IC. And again, that contributes to design reuse, because now someone can take this functional block and reuse it in another design and know what they need to do to change it to reuse it in another design. In addition, it allows someone to really thoroughly review what I've done and the choices I've made. Are my equations right, and are the values I selected correct? And here's another kind of measure of what is a functional block. And this is the biggest benefit to this. How many data sheets does it take to review this portion of the schematic? It takes one data sheet. Okay, so what we do at 3M is, I hate, and this doesn't happen at 3M, I hate getting an email from another engineer that says, oh, I got a schematic design review on Thursday and it's Monday. Can you participate in the review and review my design? Here's my schematics. And it's 30 pages of schematics. I don't have the time. I feel very conflicted because I want to review them, but I don't have the time to thoroughly review 30 schematics. And so what we do at 3M is we take that design and we give each engineer that's reviewing the design 3 schematics. And because they're functional blocks, because the outside connectivity kind of doesn't matter, because they need one data sheet, they can really thoroughly review that portion of the circuit. Connectors, oh my gosh. I accidentally got copied on an email between 2 engineers that were saying not so nice things about me devoting entire schematics to connectors. And I get it. I mean, I'm notorious for taking a design at 3M that was 15 schematics and turning it into 30. But connectors are the doorways to your design. And they can really be the weak points of your design. And part of your design review process should be to look at the design and say, are my connectors well covered? Do they have ESD, EMI, EMC mitigation? And if those connectors are spattered throughout the design, contained in other schematics, that becomes really difficult to check off that box on the design review process. Do not do, and I was, like it was communicated, I was scrambling on getting my my presentation done. There should be an X over this one on the VCC. But give your power nets descriptive names, that tell you information about, and these are pretty benign voltages, but if you're dealing with a board that has higher voltages, well, this is what you're going to use to set up your creepage and clearance requirements for your PCB. So if you just have VCC on there, how do you do that? Well, you got to go back and you got to, I don't even know. Just label it with the voltage on there. I think this is really a relic of the day prior to Altium, when it was hard or challenging to easily import critical information about components into schematics. And I see this. I see a schematic component with only the value of the capacitance visible in the designator. And the idea is that you would go to the bill of materials, and that's where the detailed information about the component would be. It's easy to do now. And again, it goes back to that whole reviewing process and contributes to people more easily and robustly being able to review your design. If they can see the wattage on a resistor, if they can see the voltage that a capacitor is rated at and the voltage of the rail it's on, they can determine whether that's an appropriate capacitor choice. You know, I displayed the tolerance for this 10K resistor, and I wouldn't do that on this rail, but if this were something in RF or, you know, something where it was critical that a resistor have a tolerance visible, put the tolerance and make that visible too. The other thing I want to bring up at this point too is, as PCB designers, it's been my experience that we can be, if provided with the correct tools, we can be some of the most effective design reviewers there are. That we can catch more errors. I mean, I've seen a set of schematics go through you know, a team of electrical engineers for review, where some of those guys have been electrical engineers longer than I've been alive, and come out the other end and go to layout, and I find a ton of mistakes. And it's not, again, I'm not tooting my horn, I'm saying that just in the process of layout, I catch things. The other thing I would say is always have the footprint that you want used for that component visible in the schematic. Again, for checking and design. Because, you know, depending on how you manage your components, and I'm not going to, you know, there's a lot of different ways to manage your components in Ultium. You know, you can have multiple footprints associated with a single schematic symbol, and someone could have selected the wrong footprint and intended another one. But if you have it visible as you're doing the layout, as you're selecting that component in the schematic and cross-probing to the PCB, you can see whether or not the actual correct footprint was put into the PCB. This is another thing I see is, you know, this is a LDO, and on the left-hand side here is how I would not do it. But you see it a lot, where people just put the designator and the part number. Why not put the voltage, the output voltage, the current that it's capable of, and the footprint? And I mean, this is a pretty short description, but for all of my ICs, I have two descriptions. I have the more verbose one, and then I have one that is pared down. I always make the description visible, because there's so many ICs out there that you can look at it and have no idea what it does. And I guess the idea is that, you know, if someone wanted to figure that out, they would look up the part number. But why not just put in a short description of what that component does? So I hope that in the presentation, I have communicated a couple of ways, you know, that you can create these essential elements and the benefits of having these essential elements in your schematics. I would love to hear, you know, if anybody has any additional suggestions I can add to this presentation. I would love to hear those suggestions, so, you know, please communicate them to me. I would like to thank a couple of people, or more than a couple of people. You know, Marty, who's no longer at Ultium, I've never met Marty in person, but I've watched so many of his videos. And the funny part is, at the University of Minnesota, I got introduced to Ultium Designer, and I was, oh, I loved it. I was working Eagle, and so, you know, Ultium was a good experience for me. But I literally started watching Marty's videos, and then 6 months later, I was teaching classes at the University of Minnesota on how to use Ultium Designer. And I think that is a testament. And then also Ben Jordan, I've watched a ton of his videos as well. The Ultium community, oh my gosh, there are some absolute rock stars on the Ultium community that are willing to help out. And I still, encounter things with Altium Designer that I don't know how to resolve, and I have to go to the boards. And it always amazes me the amount of time and effort these guys are willing to devote to answering other people's questions. Robert, the FIDEVL courses, again, I would highly recommend them. And I'd like to thank Jim Carlson, who's here from 3M with me, who had to listen to my dry runs on my presentation until 10 o'clock last night. And then Dan Beaker and Rick Hartley are two people that I've learned a tremendous amount from. And I'd like to thank Altium for making an awesome tool. So that's my presentation. Thank you.